Hi, in this lecture series I will be presenting X-rays and X-ray diffraction rudiments. X-rays were discovered in 1895 by a German physicist Röntgen. So at that point this X-ray was totally a new radiation and its properties and nature were not known. Because it was absolutely unknown, since its behavior was absolutely unknown, scientific community gave its name unknown radiation, that is X radiation. Then they started working on what are the various properties or behavior exhibited by this radiation, and they started comparing the behavior exhibited by this radiation with visible light and found that some of the properties were similar to visible light, whereas some of them were dissimilar. For example, some of the similarities they observed were this radiation also start or travel in straight line, and it exhibit or it can expose photographic plate when it is allowed to fall on. So it shows photography or photographic property. And a few of the dissimilarities they noticed were, first one is, so this radiation is absolutely invisible, and another is this X radiation is found to be highly penetrating. It is having very high energy and it can penetrate through flesh, human flesh, or it can penetrate through a thick piece of wooden block, even a metal block through which this X radiation can pass through. So that is another dissimilarity they noticed, penetrating power. So because of these two properties, that is this, it can expose photographic plate when it is allowed to fall on, and it can penetrate through a thick metal block. So these two properties were highly fascinating for scientific community. So they started analyzing this and they found that this radiation will be very useful for few applications or some of the applications. Correspondingly, without having a clear picture about this radiation, they started using this unknown radiation X-ray, and a new concept is coming into scientific science, that is X-ray radiography. So in this X-ray radiography, what they have done is they kept an X-ray source on one side of the material or a block, and a photographic film is arranged on the other side. And this X-ray radiation which was produced on one side of this block was allowed to pass through this material, and it falls on this photographic film. So when this photographic film was developed, they found that there is some variation in intensity, that is the intensity of X-ray falling on different parts of the photographic film are different. So this could be because the X-ray, when it is passing through this according to the variation in density of the material, the X-ray may be allowed to pass through or may be blocked, and it was found that the less dense region allows more X radiation, whereas dense region comparatively blocks X-ray radiation. So therefore this photographic film or the image what we are getting here is a signature of the density variation within the material. So because of this idea or this concept, they understood that this radiation could be used for detecting maybe cracks in the metal blocks, or maybe fracture, that bond fracture, etc. could be revealed. So that is how this radiography came into scene. So without knowing this, without having an approximate idea about this X-ray radiation or a clear picture about X-ray radiation, this radiography continued, and this continued for more than a decade, about 15 years or more. This radiography continued without having a clear information about X-ray, and it was in 1912 the absolute nature of X-ray was completely established, and X-rays were diffracted by crystals, or X-ray diffraction studies were carried out by low A, which proved beyond doubt that X-rays were waves. That is, wave nature of X-ray were established in 1912. So that completes the picture that X-ray is now clearly known. So this basically the diffraction is a phenomenon exhibited by waves. So X-ray, where X-ray was diffracted by crystal, means X-ray should exhibit wave nature. For example, sound is a wave, light is a wave, they also undergo this diffraction. When I am talking here, I make sound, and this sound goes through this door and it is getting bending, and it reaches the next room, and the person who is standing in that region, he can hear my sound. On the other hand, the same person, he cannot see me, because even though the light is getting reflected from my face and it tries to go there, but this obstacle is quite big for light. By definition, diffraction is the bending of the wave at the edge of an obstacle. So for the diffraction to take place, the size of the obstacle should be comparable with the wavelength of the wave. So that is a peculiarity. That is, from this experiment we understand that X-ray is getting diffracted by the crystal. That means it will, that is the size of the diffracting object should be comparable with the wavelength of the wave. So we will get an approximate idea about what should be the size of X-ray wave. So in the case of sound wave, we have the expression V is equal to f lambda, where velocity of sound is 340 meter per second, and if I take the frequency of my sound as approximately 1 kilohertz, say 1000, so I will be able to find out lambda. So this lambda comes around 0.34 meter. That is, if the size of the obstacle is around 0.34 or around 0.5 meter, half a meter, then that obstacle cannot block my sound. So the sound will bend around and it will go to the distant point. On the other hand, when we speak about the wavelength of light, visible light, the wavelength range is 3500 angstrom or 4000 angstrom to 8000 angstrom, where we use the unit angstrom for representing the wavelength of light, because it is very small value, and this 1 angstrom is approximately or is equal to 10 to the power minus 10 of a meter. So this is very small. So that is why the obstacle, when the light is getting reflected from my face, that cannot reach the other room, because this door or that boundary, that is quite big for light to bend. So approximately what I am telling is, so through this diffraction we will be getting the picture about what is the size of the wave. And in X-ray diffraction, the X-rays are diffracted by the crystal, and in X-ray diffraction, X-rays fall on crystal plane, and from two adjacent planes the X-ray is getting reflected back, and these reflected X-ray or X-ray waves, they get superimposed and we get a constructive interference, and it is a constructive interference, that is what we call it X-ray diffraction. Therefore, in the case of X-ray diffraction, the obstacle is the interplanar spacing. It is the interplanar spacing which decides whether this wave will be reflected or not. Therefore, that interplanar spacing is approximately 0.5 angstrom to 2.5 angstrom. So this X-ray diffraction is possible only if, or only that particular X-ray beam which is having a wavelength in this range will be diffracted by the crystal. So we get an approximate picture about what is the size of X-ray wave that was used. At present science, we know that X-rays are electromagnetic waves. So there is wave, basically wave is something which carries energy, that is by the process of particle vibration. If we consider mechanical wave, a mechanical wave is having particles which are vibrating, and because of this vibration energy is transmitted handed over or transferred from one particle to the next, and in that process the energy is transmitted. So here X-rays are electromagnetic wave, and it is having wavelength, it is ranging from 0.1 angstrom to 100 angstrom. So it comes in electromagnetic spectrum. So we have electromagnetic spectrum. If you mark like this here, maybe starting with radio waves, then we have got microwaves, then we have, after microwave we have infrared waves, then we have visible light, then we have got UV radiation, then X radiation, then it goes gamma. And this electromagnetic spectrum sometimes we will mark in terms of wavelength or in terms of frequency or in terms of energy. For example, the wavelength of gamma is less than 0.1 angstrom, and for X-ray the wavelength range is from 0.1 angstrom to approximately 100 angstrom, and UV rays it is 100 to 4000 angstrom, and visible radiation it is from 4000 to 8000 angstrom, and infrared from 8000 to 10 to the power 7 angstrom, and microwave it is 10 raised to 7 to 10 to the power 11, and this is more than 10 raised to 11. So this is the range of wavelength for different electromagnetic radiations or spectrum. And the same thing can be expressed in terms of frequency. If you want to express in frequency, then we use the expression that is C is equal to F lambda. So F is equal to C by lambda, where C is 3 into 10 to the power 8 meter per second. So that way also you can express this in terms of frequency, or you can write in terms of energy, E is equal to hc by lambda or h nu. So when we express in energy, that will be given in terms of electron volt. So any standard textbook you can go through and you can see that this electromagnetic spectrum is given either in wavelength order or in terms of frequency or in terms of energy. If it is in energy, it will be given in terms of electron volt. Electron volt is the unit of energy which is used because 1 electron volt is the energy acquired by an electron when it is moving through a potential difference of 1 volt. So any of these can be used. So our interest is here X-rays, its wavelength range is 0.1 angstrom to 100 angstrom. So this is not a sharp boundary. 0.1 angstrom or 100 angstrom is not a sharp boundary for X-ray. For example, this 0.1 or in this range, when you get an electromagnetic radiation, so that the property of electromagnetic radiation is decided by the wavelength or energy of the electromagnetic radiation. So at this point the radiation can be either X-ray or gamma ray. So whether it is X-ray or gamma ray is decided by how this radiation was produced. For example, in the case of X-rays, X-rays are produced when fast moving electron interact with the electrons in atom, whereas gamma rays are produced when there is nuclear rearrangement or nuclear modulations are responsible for the production of gamma rays. So correspondingly the same point you may get X-ray or a gamma ray. So so in this X-ray diffraction, so this is a range. So we have the range of wavelength from 0.1 angstrom to 100 angstrom, but of which 0.5 angstrom to 2.5 angstrom, this is the region which is useful for X-ray diffraction by crystal, whereas other wavelength, that is as the wavelength decrease its energy increase or frequency increase, and as we go towards this, so this is a high energy region, towards this side the energy gradually decrease. So this is a region we are interested in X-ray diffraction. So We have got two applications. One is X-rays can be used for X-ray radiography, and another is X-rays can be used for X-ray diffraction. So, in X-ray radiography we can reveal maybe bone fracture or crack in a metal, something like that. So, that size of the order of approximately 10 to the power minus 3 meter. So, a crack which is nearly about 1 millimeter or less. So, those type of distances or a small size could be revealed through this radiography, whereas in X-ray diffraction we can go further down, that is we can go even down to around that is in diffraction we can go down to 10 to the power minus 10 meter. So, that is the advantage of X-ray diffraction. So, X-ray diffraction can reveal a very small distance up to the size of 10 raised to minus 10 meter, so that we will get an information. So, inside the crystal or the nature of the crystal or nature of crystal structure, material, etc., can be revealed through this X-ray diffraction. So, it became a powerful material science tool. Now, we want to understand this electromagnetic, X-ray is an electromagnetic radiation. So, we want to understand how this electromagnetic radiation carries energy, how we can detect this energy. So, these things are to be understood before getting into the detailed study of X-ray diffraction. So, basically a wave is something which carries energy. So, electromagnetic waves, they also carry energy. So, how does this electromagnetic wave carry energy? So, as I have mentioned earlier, in the case of a material wave, it is because of the vibration of particles, whereas in electromagnetic wave there is no material particles. So, this wave can even travel through vacuum. So, in electromagnetic wave, it is the variation in electric and magnetic field variation which propagate through space. So, we say that there is electric field, suppose say electric field and magnetic field. So, this is electric field and this is magnetic field, and electric and magnetic field will propagate through space, which and the direction of propagation is perpendicular to the electric and magnetic field. So, how we can perceive it? So, when electric field, so we use this electric field to see objects around, or X-ray is an electromagnetic radiation. So, in all these cases, this electric field, it is an electric field vector of this wave which interact with matter, and that will be more useful. So, generally when we study this interaction of electromagnetic wave with matter, we are not much interested in magnetic field. So, we are interested in only electric field. So, it is a electric field which will give complete picture. So, in electric field again, this electric field, if we take electric field is in the y direction and the propagation is in the z direction, which is the direction of E cross H, which we study in electromagnetism. So, electric field E in the y direction is not a constant electric field, that is it continuously vary in the positive and negative y direction, that is with respect to the 0 there will be vibration or the variation in electric field. So, this electric field varies with respect to time as well as with respect to space. So, if you take any particular instant of time and if you study the electric field along the x axis, there will be variation in electric field. If we take a particular space and if we study the electric field with respect to time, then also there will be variation in electric field. Both electric field will vary sinusoidally. So, generally if we mention or mark the variation in electric field, we can write electric field as E is equal to A sin omega t minus kx, where omega is the angular frequency and k is the wave vector, or we can represent this in the form A is A sin 2 pi into nu t minus x by lambda. So, where nu is the frequency and lambda is the wavelength, and this nu t mention that there is variation in with respect to time, and this represents there is variation with respect to space. So, if we draw it, so electric field E with respect to time, if you plot, the graph will be of this pattern. So, this is maximum electric field, we call it E plus, this is minimum, we call it E minus. Same is the case with variation in electric field with space variation or distance. So, here also we will be getting a sinusoidal variation. This is 0, this is plus E and this is minus E and this is your x, and in this case this distance is your wavelength. So, electric field varies with respect to time or with respect to space. So, in this process, because of this variation in electric and magnetic field, the energy will be propagating, and this X-ray energy or the energy of the radiation is measured in terms of its intensity, in terms of intensity of the radiation. Intensity of the radiation is the total energy which propagates through one unit area arranged perpendicular to the direction of propagation in 1 second. That is, it is the rate of propagation of energy normally through unit area. That is what the intensity, which talks or which gives an information about what is the energy advancing, and that is energy per area per second. Therefore, naturally its absolute unit will be joule per meter square per second. But normally this measurement is quite tedious. Therefore, in X-ray measurement we do not go for this absolute measurement, instead we go for relative measurements. So, in relative measurements, for example, if we go for X-ray diffraction, maybe X-ray counts will be taken and we represent it in arbitrary units. We call it AU, A dot, that is arbitrary unit. If we go for X-ray radiography, we will use maybe that is a relative blackening of the photographic film, that may be used to represent what is the total energy advancing. So, that is so now we are getting some picture what is how X-rays produce or how this X-ray is carrying energy and how that energy can be measured. Now, the question is how these X-rays are produced or how electromagnetic radiation can be produced. So, we if we go through any standard electromagnetism textbook, we will come across that is the production of X-rays through the accelerated charge particles. Accelerated charge is the source of electromagnetic radiation. So, in these undergraduate physics textbooks, the chapters are graded in a particular form, that is first maybe static electricity, second unit generally it will be current electricity, then comes magnetic effect of electric current, then electromagnetic induction, and then comes electromagnetic waves before optics. So, in static electricity we speak about a stationary charge and around which there is stationary electric field. That is, if we take a particular point at a certain distance from the charge, we will have a fixed electric field. Whereas in current electricity we speak about the charge start moving, charge is moving with constant velocity. When charge is moving with constant velocity, we say that current is produced and the distance to the point from the charge is varying. So, naturally there is a variation in electric field, and we say that around a moving charge or a current there is uniform magnetic field. That is, a varying electric field produce a uniform magnetic field. Again in the next unit when we move, then we come across electromagnetic induction, where the variation in magnetic field again produce electricity back. So, that is, if a stationary charge is there, there is a stationary static electric field. If charge start moving with constant velocity, you have got a varying electric field, that is a constant magnetic field, and if the charge start moving with uniform acceleration, we will have a varying magnetic field which will produce an electric field. That is, the electric and magnetic field, there is a sustained variation and this will propagate the energy through space. This is how electromagnetic wave is produced. So, in X-rays this is high energy, therefore, the acceleration or deceleration, this should be of very large value. Therefore, for the production of X-rays, X-rays will be produced in X-ray that is tube. In X-ray tube it is a evacuated chamber, there will be two electrodes. One is an electrode, there is a positive electrode and a negative electrode, a cathode, which is also the source of electron and which is kept at a very high potential, and anode will be kept at a reasonably low potential or it is at 0 potential, and a very high potential difference will be produced. And the thermally heated tungsten filament, that will be producing electrons, and this electron will be getting repelled by this negatively charged electrode and it will be accelerated. So, when it is moving at a very high energy, sometimes the potential difference of the order of 30,000 volt will be given, and the corresponding the velocity acquired may be of 1/3 of the velocity of light. Such a high speed electron, when it gone collide with the target, suddenly it will be decelerated and the energy will be released. That energy, when it is converted, major part of the energy will be in the form of heat, and a portion may be less than a small, maybe 1% or so, will be converted into X-rays. So, this production of X-ray we will be seeing in depth in the coming lecture. And also another point I like to mention here is in the case of this X-ray, that is here we say that we speak in terms of classical picture, that is energy is transmitted in the form of wave. But when we speak about X-rays, visible light, all the phenomena exhibited by light cannot be explained with this concept of wave nature. So, later point in the 1900s we came across a new concept, we call it quantum theory, according to which when light is advancing through space, it is not only the wave, sometimes we can also speak in terms of the packet of energy which is advancing. So, many packets of energy is advancing, and this energy packets are represented by E is equal to h nu. This is a beautiful expression in physics and which connect this classical physics and quantum physics. So, here h is Planck's constant, which is 6.62 into 10 to the power minus 34 joule second. So, if we speak X-ray or this radiation in terms of photons, we can say that this h nu is advancing, many h nu pieces are advancing. But when we speak in terms of wave, then it is having frequency, wavelength, etc. So, therefore, this h nu together speak about quantum nature, whereas nu speak about the wave nature, so classical nature. So, this classical picture and quantum picture together explain the many behavior exhibited by this radiation, and thus this unknown radiation became absolutely known radiation, and its production and its spectra will be discussed in next lecture. Thank you.